Okay, let's look at some examples, simple examples. Let's say if I have a input signal going through a typical first order system with transfer function. So input signal is a 3 sinusoidal signal. Sine 10t plus sine 100,000 t plus sine 10,000 t. So what would be the frequency spectrum look like in magnitude? Or how can we solve this or find this? Well, first of all, if you use the same approach like before the second midterm, sinusoidal in, sinusoidal out frequency response function A sine omega t through a transfer functions S. Output will be input amplitude times the magnitude of frequency response function, another sinusoidal signal with a phase shift, which is the phase of this frequency response function. And in other words, S equal to I omega. So in that case, if this is typical first order system, so the magnitude will be 10 real imaginary 0.1 times omega squared. And you can put it here. Or you can use the concept of filter. This is typical low pass filters. In other words, the gain is 10. Everything below the cutoff frequency. Cutoff frequency is 1 over tau. So tau is 0.01, so 100 radian per second. 100, 10 times, that's 1,000. 10 more time, 10 times more, 10,000. This is omega. So low pass filters. So you should have this should be 10, but in dB scale, that should be in 20. Okay, so now what's the frequency? Input frequency at 10,000, 10,000. So what's 10? Where's the location at 10 in the Bode plot? That's right here, 10. In other words, in this case, the gain will be 20 dB, which is 10. So I can quickly put it here. The output should be input amplitude 1 times 10 times another sine 10t, another sine of 10 t plus the phase angle phi 1. Now another one, thousands will be here. So flat drop 20 dB, attenuate 20 dB in decibel dB. So in straight scale will be dropped to 1/10. So input amplitude from here 10 drop to 1/10 of 10 should be 1 times sine 1,000 t with a phase shift. Another one, 10,000. From 1,000 to 10,000, 10 times more. Another 20 dB dropped. So input amplitude is 111, so 111 times drop 1/10 times sine. Okay. So if you use the concept of filters, okay, you can get this quickly. Or you can plug in omega at 10. Here, you get these numbers. Omega got 1,000, put it in, you got these numbers. This one, you got this number, almost same. Okay? But I like you to use the concept of filter and to get this one. Let's look at another example. So, if I have signal sine t plus sine 50t plus sine 1000t, I want to reduce or attenuate this low frequency component as well as high frequency component and keep this center one. So what type of filter do we need? We have this one going to filter, and you want to keep this one and attenuate these two with 20 dB attenuations. So what type of filter do we need? When we talk about filters, so what's the cutoff frequency? We want to keep the center frequency, attenuate low and high. So of course we need a bandpass filter. And if we need a bandpass filter, and what is the corresponding cutoff frequency? In this case, you should have two lower frequency and high frequency. Well, if you use the concept of bandpass filters, so bandpass filters, one, two, three, four. So if I pick somewhere 50 hertz, somewhere here. So first of all, bandpass filters. You should have this body plot. Okay, so if I said I have a 50 hertz, 50 radian per second is a signal frequency. I want to keep this one. I want to reduce this one. So I should have a bandpass filter. So what will be the cutoff frequency? In other words, what will be this frequency? What will be this frequency? Well, if we pick, let's say we pick this frequency at 10 radian per second. Why? Because 10 of this input frequency, so 1, the slope is 20 dB per decade. So from 1 to 10, the difference here, you get 20 dB. So 50 in somewhere here. So this one should works. Now, How about I pick this point at 100? Why? 10 times less of 1,000. So from 100 to 100 to 1,000. 1, 2, 3. Yes. What's the difference? Again, another 20 dB. In this case, is minus 20 dB per decade. This case is positive 20 dB per decade. Okay, so if that's the case, my cutoff frequency 10 and 100, it will be able to satisfy our 20 dB attenuations. So we keep the center frequency of 50, attenuate 1, and 1,000 radian per second frequency components at these two frequencies. Okay, keep it in mind when we say filters. When we say filter, we don't really filter the signal out. We just make it less important. We attenuate that. Okay, for example, this one here, we just have the numerical number. Originally, these three signals at three different frequencies, they are equally important because it's amplitude 1 and 1 and 1. But after this system filters, what happens? The amplitude is 10, 1, and 0.1. The higher frequency, the amplitude get to dropped. So now 0.1 compared to 10 is nothing. Okay, so we didn't make it disappeared. We just make it less important, attenuate the signals. That's what we call filters. Okay. So what if we want to have more attenuation? So ideal attenuation in terms of Bode plot, you should have, if we say the low pass filter, this is the first order, 20 dB. Ideal case should be flat and drop totally. That's the ideal. However, in reality, it's not possible. So all we can do is we make the slope more stiff from 20 dB per decade to 40 dB and then to 60 dB. Okay, so if we want to get large attenuations, make the slope steeper. So one of the easy way to do is you just have two first order in series, then you get 40 dB attenuations. Okay, so if I have, for example, low pass filters, so we can make these this one, another one. Oh, let's say resistance and capacitors. In other words, you can see this one right here, one, this one, another one. So overall transfer functions. So V out over V in. Oh, out, V in. You should have this is first order, another first order from this point. So you have times minus I. Because this between this would be this one. Another one. To give you this. Typical second order system, and the slope will be 40 dB. Also the gain will be square, and 1 that's 20, so square 40. You get more attenuation. However, keep it in mind, this one, the new cutoff frequency at 3 dB will be different, okay, will be a little bit different. So you can solve this one, solve this. So Cn equal to 2 minus 1. See? In other words, you have higher order system second, and you get another one. Okay? So you have n equal to 1 as first order, n equal to 2 second order. You can apply the new to get a new cutoff frequency. Why is that? Because if you had 20 dB, it's a curve like this, 20 dB, and then you have 40 dB, so a little bit more, and then you have 60 dB. So the slope keeps changing when you increase the order. So the cutoff frequency will change. So here's the new equations to find the cutoff frequency. Okay.